Hello, everyone. I'm Weicheng Wang. I'm glad to introduce our work, Interactive Search for One of the Top K. I will show our work by 5 sections. First, introduction. Suppose that user Alice wants to buy a used car. Here is a used car dataset. Each used car is described by 2 attributes. Here we assume that if the value is larger, it is more preferred by a user. One example is the horsepower of the used car. Now, the problem is, which used car should Alice buy? There are some popular queries for this problem. For example, the top K queries and the skyline query. In this talk, we will focus on the top K query. Assume that Alice has a utility function in her mind. The utility function represents Alice's preference. Suppose the utility function is 0.4 multiply x1 plus 0.6 multiply x2. Based on this utility function, the utility of each used car can be obtained. Based on these utilities, we can find Alice's top K used cars. That is, the K used cars with the largest utilities. For example, suppose K is equal to 2. Then used car P1 and P3, which have the largest utility, are the top K used cars. However, in practice, we do not know the user's utility function, and thus it's hard to recommend to Alice her top K used cars. Motivated by this, we try to utilize user interaction. We interact with the user for rounds. At each round, we present 2 tuples, 2 used cars to Alice, and asked her, which one do you prefer? Based on Alice's feedback, we can understand her utility function better. With more rounds, with more questions asked, we could know Alice's utility function more. Then, based on the learned utility function, we are able to recommend used cars to Alice. Thus, our problem is interactive search for one of the top K. Given a point set, we are to ask Alice a number of questions and return a used car, which is one of her top K used cars. Note that we return one of her top K instead of all records in her top K. This is because in practice, it is enough to have one of her top K. This was supported in our user study. Besides, if we aim to find all the top K used cars, it requires heavy user efforts during the interaction. For example, Alice may need to answer many questions. In our user study, we need to ask 20 questions if we want to obtain all top 20 cars. But we just need to ask 5 questions if we want to obtain one of the top 20 cars. Thus, returning one of the top K could reduce user effort during the interaction. There are many related works. The first one is active ranking. It learns the ranking of tuples by interacting with the user. Another one is preference learning. It learns the user's utility function by interacting with the user. Obviously, both these related works utilize user interaction. As for the differences, active ranking needs to learn the order of all pair of tuples, that is, the ranking on all tuples. While we just learn the order of some pairs of tuples, the ranking on some tuples. As for the preference learning, it focuses on the user's utility function without considering the characteristics of one of the top K in our problem. While we utilize the characteristics of one of the top K in our problem to reduce the total number of questions asked by considering both the user's utility function and the tuples in the dataset. As we can see, compared with our problem, existing work need to ask the user much more questions. Our contributions are as follows. First, we show the lower bound on the number of questions asked. Then, we conducted a case study to show that returning one of the top k tuples is better than returning all top k tuples. We measured these two cases by the number of questions asked and the user's satisfactory level. We present three algorithms. First algorithm 2DPI, which works when there are two attributes. And another two algorithms, HDPI and RH. They work for general cases. Now I'm going to show our algorithms one by one. First, algorithm 2DPI. This algorithm has two major steps. First, pre-processing. We define the domain of all the feasible utility functions as a utility space. Then we divide the utility space into a number of partitions. Each partition is associated with a point. This point is one of the top k points with respect to any utility function in this partition. Then the second step is interaction. We ask a user a number of questions, each showing a pair of points to locate a partition containing the user's utility function, where the associated point of the remaining partition is the output. Now let's see the two steps in detail. The utility of a used car can be represented in this way. Without loss of generality, let us assume U1 plus U2 is equal to 1. Then we can represent the utility of each used car by only U1. In this way, we can plot the utility of each used car as a function of U1. For example, the utility of P1 can be represented as 1 minus U1. Then we can draw a line segment in this figure to show the utility of P1. Similarly, we could draw a line segment for each other used cars. Now, let us see the ranking of points with respect to each utility function. Suppose the utility function is 0.4 multiply x1 plus 0.6 multiply x2. Then we can directly calculate the utility of each used car. Based on these utilities, we can directly rank all these used cars. First, used car P3, which has the largest utility. Then P1, P2, P4, and finally, used car P5, which has the smallest utility. Now, let's see how to derive the ranking from this figure. We first build a vertical line across point 0.4, 0. This vertical line intersects with the line segment of each used car. Let's check the order of intersections from top to bottom. This vertical line first intersects with the line segment of P3. Then it intersects with the line segment of P1. Next, P2, P4, and finally, it intersects with the line segment of P5. As we can see, the order of intersections from top to bottom is the same as the ranking of the used cars. In this way, it is easy to see the ranking of points with respect to each utility function in the figure. Suppose we have a utility function now. Then we just need to build a vertical line across point U1, 0. Then we just need to check the intersections from top to bottom, and we can obtain the ranking of the used cars. For example, consider this right range. For any utility function where U1 is in this red range, the vertical line will first intersect with the line segment of P1. Thus, we can conclude that P1 has the largest utility. Now, Based on these properties, we can start our pre-processing. We call the possible range of U1 the utility space. Given parameter k, we divide the utility space into several partitions, such that each partition is associated with a point which is among the top k points with respect to any utility function in the partition. For example, suppose k is equal to 2. Then we can divide the utility space into two partitions, this red one and green one. As we can see, P3 is one of the top 2 points with respect to any utility function in this red partition. And P5 is one of the top 2 points with respect to any utility function in this second partition. Now we go to the intersection step. We have divided the utility space into several partitions. Each partition is associated with a point which is among the top k points with respect to any utility function in the partition. Now, we interact with Alice to locate her utility function in a single partition. Let's see in this figure. We can see P3 has a larger utility than P5 with respect to any utility function in the first partition. And P5 has a larger utility than P3 with respect to any utility function in the second partition. Thus, we can ask Alice a question. We just present tuples, or say used cars P3 and P5 to her and ask Alice, which one do you prefer? If P3 is better, then we conclude that Alice's utility function must be in the first partition. If P5 is better, Alice's utility function must be in the second partition. Now we locate her utility function in a single partition. We just need to return the associated point of the partition. For example, suppose her utility function is in the first partition, we just need to return P3. If her utility function is in the second partition, we just need to return P5. Our algorithm, 2D-PI, is asymptotically optimal in terms of the total number of questions asked. The second algorithm is HD-PI. This algorithm is similar to algorithm 2D-PI. It also has 2 steps. First, pre-processing. We divide the utility space into a number of partitions. Each partition is associated with a point. This point is one of the top k points with respect to any utility function in this partition. Then we interact with a user. We ask a user a number of questions, each showing a pair of points until there is only one partition left. Then the associated point of the remaining partition is returned. Now let's see these 2 steps in detail. Consider 3 attributes. The utility function can be represented in this way. For simplicity, we represent each utility function by a utility vector, U1, U2, U3. Without loss of generality, let us assume U1 plus U2 plus U3 is equal to 1. We call the possible range of the utility vector the utility space. As we can see in this figure, we can draw the utility space. This pink range, this pink triangle, is the utility space. Given the parameter k, we can divide the utility space into several partitions, such that each partition is associated with a point, which is among the top k points with respect to any utility function in the partition. For example, for this utility space, we can divide it into 5 partitions. And for example, this yellow partition, Q1 is one of the top k points with respect to any utility function in this partition. And Q4 is one of the top k points with respect to any utility function in this purple partition. Next, we go to the intersection step. We have divided the utility space into several partitions. Now, we are going to interact with Alice to delete the partitions which cannot contain her utility function. Suppose we have two tuples, two used cars, P2 and P3. Then we can build a hyperplane consisting of P2 and P3. In this figure, this red line is a hyperplane. This hyperplane divides the utility space into two halves. Each half contains some partitions. Now we ask Alice, which one do you prefer? Based on Alice's answer, her utility function can be located in one half. For example, in this bottom half. Then the partitions in the other half can be deleted. In this way, we interact with the user until there is only one partition left. Then we return the associated point of the remaining partition. The last algorithm is RH. For this algorithm, it does not have any pre-processing phase. For the interaction step, we keep a region representing all feasible utility functions in the utility space. Then we keep asking a number of questions, each involving a pair of points. Let's us show in a flowchart. Suppose we ask a question. Then, based on the user's feedback, the region containing all feasible utility functions will be shrunk. Then we check whether we can find a point which is among the top k points with respect to any utility function in the region. If we can find such a point, then we terminate and return this point. Otherwise, we ask another question. In our experiments, we conducted our experiments on synthetic datasets and real datasets. We compared our algorithms with existing algorithms, active ranking, utility approx, preference learning, UH-random, and UH-simplex. We measured these algorithms by the number of questions asked, that is, the number of interacting rounds. As we can see in the experimental results, our algorithms ask the least number of questions. In conclusion, we studied a problem interactive search for one of the top K. We proposed algorithms 2DPI, which works when there are two attributes, and algorithm HDPI and RH. Finally, we conducted experiments to show that our algorithms are better than the best known existing algorithms. Thank you very much.